Last lesson we discussed the magnetic field generated by an electric current. But we know that an electric current is caused by the motion of electric charges. Therefore, it is reasonable to assume that there is a magnetic field associated with a moving charge. And that's what we will be discussing in this lesson. A moving point charge is equivalent to an electric current, and therefore when moving charges constitute an electric current, the motion of charges generate a magnetic field. The magnetic field B at a point R from a point charge. Now we're going to have a quantitative expression. Suppose we have a charge Q. Let's say we need to find the magnetic field at this point due to this charge Q, and this Q, the charge Q is moving with a velocity V. The magnetic field generated by the motion of this charge at a point distance R, this distance is R, from that charge is given by B equal to mu 0 divided by 4 pi times QV over R squared. And we will be coming across this quantity quite a lot. Mu 0 is a quantity that we will see as we move on. So we got the magnetic field is directly proportional to the quantity Q times V and inversely proportional to the square of the distance from the moving charge to the point. And this distance R is a vector that points from Q to R. And mu 0 over 4 pi is the constant of proportionality, and mu 0 is called the permeability of free space. Now, towards the end of this lesson, we will talk more about this. Mu 0 has an exact value given by mu 0 equal to 4 pi times 10 to the negative 7 Tesla meter per ampere, which is the same as 4 pi times 10 to the negative 7 Newton per ampere squared. And this you need to keep in mind, so we will be using it very often as we go on. Now, what happens if theta is the angle between the velocity V and the vector R? Then the magnitude of B can be written as B equal to 10 to the power of negative 7. Now, where does this value come from? You know that mu 0 has an exact value 4 pi times 10 to the negative 7. If you divide this quantity by 4 pi, you get 10 to the negative 7. So mu 0 divided by 4 pi has an exact value of 10 to the negative 7. So, if theta is the angle between V, the velocity of the charge, and the vector R, then the field at that point, B, is 10 to the negative 7 times QV sine theta over R squared. Now, here is an illustration of the magnetic field produced by a moving charge. The moving charge, look at the vector R. The moving charge produces a magnetic field given at this point. Watch that carefully. Let's solve a simple problem. A point charge of magnitude 4.5 nanocoulomb is moving with a speed of V equal to 3.6 times 10 to the 7 meter per second along the line y equal to 3. Along that line, find the magnetic field at the origin produced by this charge when it is at the point negative 4, 3. Well, we have actually everything that we need to do this problem. First of all, At the instant when the charge is at this point, we need to obtain the vector r. What is the length of this vector r, where x equal to -4 and y equal to 3? The length of that vector r will be 5 meters. And if you know the length of that vector, now what is the angle theta between the vector r and the velocity v? How do you find that angle? Sine theta will be equal to 3/5, and therefore theta will be sine inverse of 0.6. Is that right? So we got the value of sine theta there, and b therefore is 10 to the -7 times qv sine theta over r squared. We know the value of q, we know the value of v, and we know the value of r, and that gives you the magnetic field as 3.89 times 10 to the -10 Tesla. Very simple problem. Well, what is the direction of this field? This field is perpendicular to both x and y axes and is directed along the negative z direction. In fact, the direction of this field is into the board, into the whiteboard that I'm using. So we can write b equal to -3.89 times 10 to the -10 Tesla K. Well, in the last lesson we discussed briefly about the magnetic field generated by an electric current. In this lesson we will make it more quantitative. We will obtain an expression for magnetic field due to current in a straight wire. Now, since current is caused by the motion of electric charges, it is obvious that if a wire is carrying a current, there will be a magnetic field around it. We saw that in the last class. Alright, let's consider a small length dl of a conductor carrying a current I. Here is a conductor carrying a current I in the upward direction here. And take a small length dl of that conductor. P is a point distance r from dl. Now here is the point P, and the distance of that point P from dl is r. And the r makes an angle theta with the direction of the current. The magnetic field dB at P due to the current I in the small due to the current in the small segment dl is given by dB equal to mu0/4 pi. Familiar? That is a constant of proportionality. I dl sine theta over r squared. Now, this is a very famous law in physics. And we're going to use this equation to generate expressions for magnetic field. So, if you consider a very small length of the conductor, the magnetic field due to current I in it will be mu0/4 pi I dl sine theta over r squared, where r is the distance of the point where this field is obtained from the length element. The direction of this magnetic field is at right angles to both the r vector and dl. So we got that expression back here. dB equal to mu0/4 pi I dl sine theta over r squared. Now, this equation is actually known as Biot-Savarth law and can be used to obtain an expression for the magnetic field B at a point due to a straight wire. Now tell me, what does the magnetic field look like due to current in a straight wire like this? In the last lesson we talked about the right hand rule to find the direction of such a field. Is that right? The field will be concentric circles. Now, we can actually use the Biot-Savart rule to obtain an expression for the electric field at a point distance r from a conductor like this. So if I have a current I passing in this conductor, what is the electric field at a point distance r from it? It's given by B equal to mu 0 over 2 pi times I over r. I'm not going to give you the derivations of this. I'm going to give you simply those expressions. So you have a conductor that carries a current I, and if you take any plane, there is a magnetic field in that plane. And if you choose a point distance r from the conductor, this will be the amount of magnetic field at that point. And the direction of the magnetic field is given by the right hand rule. You remember that one? Keep the thumb in the direction of the current, then the direction in which you grab the conductor with the other 4 fingers. So the magnetic field goes into the board on the right and out of the board on the left. Alright, let's do another example. A vertical wire on the side of a building carries a direct current of 12.5 ampere. What is the magnitude of the magnetic field inside the building at a distance of 20 centimeters from the wire? Now, we live in buildings which are wired all over. That means we actually live in a sea of magnetic fields. Well, we know that the magnetic field generated by current in a straight conductor at a distance r from it is mu 0 over 2 pi times I over r, and that is what we obtained in the previous slide. Now, that can be written in this case, I is 12.5 ampere and r is 0.2 meter. And so that's 1.25 times 10 to the negative 5 Tesla. It's a very direct application of the formula. Now, in that case, if you have 2 conductors carrying current, now each conductor has a magnetic field. Now, don't you expect that there will be a force between these 2 conductors?